So a couple more actual design things. One more design thing that I didn't mention earlier. Boroscope info, we were looking at angle of view and then the types and so here's types of scopes. So at the top there, you can see there's some special names for certain angles of view. So that top scope looking straight ahead it's a 0 degree angle of view, right? You're looking the same direction as your line of sight. It's also known as a bottoming scope. So you can look straight down into the bottom of a hole, for instance, like a drilled hole. The other ones there, the right angle scope we talked about, 90 degrees. This one's close. I mean, here's you have your center line and it's roughly 90 degrees. You can see this one maybe is slightly forward looking, the center of that field of view there. But it's looking almost 90 degrees to that, and that's 55 degree field of view. So those are kind of your two most common configurations you'll see are a right angle scope or a bottoming scope, a 0 degree scope. But some of the others that we have here, kind of an older design, a circumferential scope. Bottoming scopes, it's really hard to make a bottoming scope with mirrors, lenses, and prisms without distortion. If anyone's looked through like a telescope, you've probably seen, or even a microscope, you see there's always a lot of distortion around the edges caused by the lenses, whereas flat mirrors tend not to do that. And so a circumferential scope or a circumference scope, those use mirrors instead of lenses, so you don't get that distortion on the outside. But what your angle of view is straight ahead at 0 degrees. But does anyone see what kind of the downside to it is? What it would cause? No? You get kind of a dead spot at the center. In fact, in this case, you actually see a very small field of view that looks straight up at the center of the scope. So it's kind of a weird view, but if you needed a straight ahead looking scope that didn't have minimal distortion around the edges, you would use these circumferential scopes. But again, they're not very common anymore. They basically, bottoming scopes, circumference scopes, they've both been replaced by video scopes at this point. And then you can see at the bottom, you can also have angled scopes where instead of looking straight up or to the side, you're looking at an angle somewhere between straight ahead and straight up. So that's the forward oblique. So you can see the angle of view here, kind of going up the middle of the field of view looks something like that. So maybe that's 30 or 45 degrees. And then a retrospective scope is where the angle of view kind of comes back towards the viewer. Where would you use any ideas where like a retrospective scope might be used? And think more recip engines where something like that might be handy. Looking at valve seats. You go in through the spark plug hole and you have this retrospective where you can look back up at the valves and the valve seats, right, that are right next to the spark plug hole. So those are kind of handy for that style of that kind of a situation. Okay. Okay. When we're looking through a scope, scopes are going to have, and the lenses are going to have what's called a focal distance or a fixed focus distance. And that is, there's going to be a certain amount of positive and negative or magnification that takes place. So at the focal point or at the focal length of a scope, the image is going to be 1:1. It's going to be full size. So in the case of this, what they're showing here is the scope would be on the left. You're looking, the tip of the scope is right here, and you're looking out to the right. And you can see about 2 inches away from the distal end of the scope or the lens, you can see, or the objective lens, I guess, you can see that it's a 1:1. But objects that are closer are going to appear bigger. Okay? Objects that are closer appear bigger, or are going to appear bigger than they are. And so when you get down to, in this case, like 1 inch away, it's going to be twice the size. When you get to a 1/2 inch away, it's going to be 4 times the size. You can see it's got an exponential increase as you come closer and closer to the tip of the scope. So things very close to the tip of the scope are going to be really big. And that's why in that video, when it was talking about measurement, that that measuring board or video scope has the ability to tell you how far away the tip of the scope is. So you can ideally, when you're taking measurements, you're going to put the tip of the scope at the focal length of the lenses for the video cameras to get the most accurate measurements possible. Now, it does have a certain amount. It can correct to a certain extent. You know, it can say, okay, the object was closer than the focal length, and it'll kind of correct. But to really make sure it's dead on accurate, you try to put it right at that focal length, and then it gives you that one-to-one image. The other part is things that are further away, you can say are smaller than what they are. So there's a negative magnification. So when you get out to twice the focal distance, it cuts that in half. So from 2 inches to 4 inches now, the object's going to look half. And this is like the mirrors in your car. A lot of people have seen the objects in mirror are closer than they appear. The mirrors in your car are not flat. They're actually a slightly curved mirror, your side view mirrors. And the items, cars that are behind you that are further away than the focal point of that mirror are going to look smaller than they actually are. And that's why they appear farther away than they actually are. Now, when they're right up, you know, crashing into the corner of, you know, your rear corner of your car, they might look bigger than they actually are. I don't know exactly where the focal distance is, but for the most part, they assume things coming up behind you are further away than the focal distance, and that's why they appear further away, because they look smaller. And so the same things are happening in your boroscope or your video scope. Not as much, you know, boroscope or fiberscope, excuse me. Video scope, there's a little more correction going on. Some of them have dynamic lenses, you know, where they can do that, or they have a wide focal lens where a large amount of stuff, you know, there's a range that's in focus. So they have a lens more similar to what's in your digital camera, your camera phone, where a lot of stuff can be in focus versus, you know, a professional photographer using a lens where there's a very specific focal distance and they have to focus it for every picture. So some vocab that you're going to need to know. So we've already talked about the objective lens in the middle here. The objective distance, it's also the focal, or is the distance between the object being observed and the objective lens. And again, that's important because you need to know the focal distance. And if your object is further away, it's going to appear small. If it's closer than the objective lens focal point, it's going to appear big. We talked about overall length of the scope. So the scope, including eyepieces and anything that. The one thing that's not included is most of these have like a rubber cup that goes on as kind of a light shield, and you would take that off to measure overall length. Inside of the boroscope, those lenses, the lens, I've got lenses here, but it could also be prisms or mirrors that relay the image from the tip of the scope back to your eye, are the relay lenses or relay prisms. So a series of optical systems mounted on the length of the scope that transmit the image, and that's to keep the light from spreading out too much and the image getting fuzzy and dim. Resolution, we've all heard about, you know, we've talked about pixels and resolution of your phone camera. So a boroscope with just prisms and lenses and mirrors has an almost infinite resolution. The limiting factor is how much detail your eye can see, right? But a fiberscope, where it's a bundle of fibers, or a video scope, they're going to have a limited resolution. The fiberscope, you know, when you have all these little fibers, when you look in the fiberscope, you're actually going to see the image is actually going to make up a bunch of little circular images. That you're looking at the tips of a bundle of fibers. It's like looking at the ends of a thing of spaghetti, right? You see a bunch of little circles. Well, those are going to be almost like pixels making up your image. So there's a certain resolution drop because of that. And then in a video scope, your resolution is going to be based on that CCD sensor or CMOS sensor, and you know what kind of resolution it is, and you know, 640 by 480. Is it high def? Is it 1920 by 1080? Is it you know, is it something in between, some other resolution? And so that's what it's picking up. Now you got to keep in mind too that you have the camera in a video scope. You got the camera on the tip that has a resolution. You also have the display, which is going to have a resolution. And there are cases where they use a very, very high quality camera, very high def camera, the display that's on there may be a lower resolution display, but it can take really high definition pictures or really high definition video that you can take over to a computer and look at on a much better display. They're balancing, you know, portability with the resolution that's available on the display side of things. Or you can plug that scope into, you know, a high def television, have a giant blown up image with a lot of detail, as long as the sensor in the tip of the scope is good. So resolution, rigid boroscope, we looked at those and defined. So, you know, basically a rigid tube that relays the image. On fiber scopes, video scopes, and then the outside of the boroscope, you have a sheathing as the covering that covers the working section to keep everything kind of contained and to keep things out that shouldn't be there, like fuel, oil, hydraulic fluid. Visual acuity, that's going back to you. How well can you see? And it's not just resolution, right? So many of you wear glasses to increase your visual acuity, okay? But there's another factor that comes into play too, and this is particularly, it tends to affect males more than females. Anyone know what I'm referring to? Colorblindness. So you have to be able to pass you have to have a certain level of color perception to be able to do NDT. So, and I am red-green colorblind, but I can still do NDT. I can see colors, I can discern them well enough to do NDT. For most areas, there are a couple where I'm limited in what I'm able to look at. Okay, so if you're doing NDT, they're actually going to do a vision test as part of being NDT certified, where they will test your acuity as well as your color perception ability. And then depth of focus. So this ties to that. Remember, a lens, or even your eye is going to have a focal point. How wide of a range in front of and behind that focal point is the sharpness acceptable for images? Okay, so if you have something that's too far away or too close, you put something really close to your eyes and it's kind of blurry, right? So you have to have stuff in focus at a range, so you can't fix that. Diopter correction, that's getting into that diopter and being able to adjust the eyepiece on a boroscope or a fibroscope to match your eyes. And that's where I was talking about some of you that wear glasses may be able to take your glasses off and adjust the diopter to match your eye. But depending on what your uncorrected visual acuity is, or what reason you have to wear glasses, you may have to use your glasses with them. The eyepiece is the end of the boroscope we're looking at. Fiber optics is an array of flexible glass or plastic fibers. Okay, higher end fiber optics are made out of glass. They're more expensive. They're also more fragile. Plastic cables, fiber optic cables, are more durable. They're cheaper to produce. However, they don't transmit the light quite as well. And so they don't transmit as bright of an image, or they can sometimes cause a little bit of blurriness in the image. So your real high-end scopes are going to use glass fibers. Your less expensive scopes are going to use those. And then those can be broken down into two different types. So you can see there it talks about a random array versus a coherent array. A coherent array, in a coherent array, we have all the fibers are aligned. So if we were just doing top to bottom, the top fiber stays at the top from end to end, right? So these fibers are all parallel in a coherent array. And those are used for transmitting images. So whatever we see, whatever goes in on the left in this case is what we would see on the right. If you're not worried about that, if all you're trying to do is transmit light up to the end of the scope and project it into a dark area, it doesn't really matter if the fibers are 100% coherent. They may cross, but they still are relatively parallel, but they're not perfectly parallel. So a random array might look something like this. So you can see where if there was an image if we were trying to transmit an image through this random array, it would scramble it on the opposite end. But if all we're trying to do is take that bright light and send it up the scope and into where we're looking, you get that. In all honesty, any modern brand new scope, they don't even use random array anymore. Again, those were cheaper at one point to manufacture. The costs of manufacturing fiber optics have come down so much that most of the time they just use coherent arrays nowadays. even for the light transmission side. And again, it's not uncommon for the image, the image transmitting fibers, the ones that are going to take that from the objective lens back to your eye. Those often are glass. And if they're trying to save a little money, they'll use plastic fibers for the light transmission. Because again, you're not worried about the fact that it might distort or reduce the quality of the image a little bit. You're doing that. But a real high-end scope is going to use glass fibers going both directions. And they're going to be coherent both directions typically. Flexible boroscope, we looked at what those are. Flexible boroscope is basically something in between a boroscope and a fiberscope, where it can use lenses and prisms, and they're able to bend a little bit, but they're very limited in how much they can. They can do a slightly curved path. You really don't see them too much anymore. Again, those were an early kind of, okay, we need to get into these spaces, and then fiber scopes came out. Then glass fibers came out. People were like, okay, these are way superior and much easier to use. And then nowadays, pretty much everything is a video scope. Focusing, changing the objective focal distance. Some boroscopes, fiberscopes, videoscopes have the ability to focus the lens. Some can do digital focusing or digital zoom as well on your videoscopes, but most of them are a fixed focus setup with just the ability to kind of do diopter correction on your eye. Image is a reproduction of an object using light, and then finally magnification. Ratio of the apparent size of an image of an object seen through an optical system to that of the actual object if you look at it unaided or aided eye. So you've all seen magnification, you just got to understand it with your scope. So that kind of is your vocab that you need to know. The big way to get familiar with it, use the terms while we're in the lab. Use the distal end term in your lab reports, use the objective lens term in your lab reports. Use the talk about diopter, and you'll get familiar with these different things. And like I said, again, objective lens closest to the object, diopter closest to the eye. The only one distal end is a little bit, that's the tip of the scope where you're working.